Hi everyone, today is the first chapter of our unit on probability. Chapter 13 is all about randomness and probability basics. So to start off, before we talk about probability, let's talk a little bit about some vocabulary that's going to be useful. So first off, a random phenomenon. It is a situation in which the possible outcomes are known, but a particular outcome is unknown. So we know what the possible outcomes are, but we don't know on a single round of that phenomenon what's going to happen. So think of flipping a coin. We know it could be heads or tails, but we don't know on a single flip what's going to happen. So a trial, that is each occasion upon which we observe a random phenomenon. So every flip of the coin, that is what we could consider to be our trial. And then the outcome, this is what we are going to record after each trial. So did it land on heads? Did it land on tails? And then an event, it is a combination of any number of trials. So maybe we're going to flip the coin 10 times, record all of that, and see what is the outcome of those 10 flips. A sample space, it is a collection of all possible outcomes from an event. So if we flip a coin 2 times, we could get heads, heads, we could get heads, tails, tails, heads, and tails, tails. That is what we consider to be our sample space. So in order to understand the basics of probability, we first have to understand the concept of the law of large numbers. And to begin with, we're going to talk about probabilities where the events are considered independent. So basically what that means is that if we have one trial of an event, it will not influence the outcome of another trial. So some examples here, if we flip a coin, what happens on the first flip will not necessarily influence what happens on the second flip. If we draw a name out of a hat and then put it back in the hat, we will not have any influence on what the next pick is in that hat. Or rolling a die, if we get a 1 on the first roll, that does not influence the likelihood of any other outcome on the second one. So when we have independent events, basically one trial will not impact the outcome or likelihood of the next trial. So what the law of large numbers says is that in the long run, relative frequency of repeated independent events get closer and closer to a single value. Okay, and I'll give you an example of that here in a moment. But basically, over time, if you do a trial infinitely many times, it will get closer and closer to a single value. So if you've taken calculus or pre-calculus, you can kind of think of it as a limit. Okay. So the single value is called the probability of the event. So that value that it's approaching, that's what we refer to as a probability. And because this definition relies on an infinite repetition and infinite outcomes, we sometimes call this empirical probability. So as an example of this, if we flip a coin and we are, say, recording the likelihood or the percent of times we land on tails, we know that if we flip a coin 10 times, it is not necessarily going to land on tails 5 out of 10 times every single time. But what the law of large numbers tells us is that if we flip 200 times, 400 times, 1,000 times, and beyond, up to infinity, in the long run, that probability or that percentage will approach 50%. And that's what we refer to as our probability. Now, one concept that we have in probability is called the law of averages. It is actually non-existent. So what the law of averages says, or the mindset behind it, is that if an event hasn't happened for quite some time, then it is bound to happen soon, okay? So let's think about this. If we flip a coin 5 times and we've gotten tails every single time, well, in the back of our minds, we might think, well, the next one's got to be tails. It's bound to happen, right? It hasn't happened for some time. But because those events, those coin flips are independent from one another, that is flawed logic. We cannot say for sure that we are more likely to land on tails the next time than heads, or vice versa, okay? So the law of averages, even though you think something should happen or it's due to occur, that is not necessarily good logic when it comes to the law of averages. So when it comes to modeling probabilities and calculating probabilities, we really have 2 options. The first one would be to find the experimental probability. So if we wanted to know how many times out of 100 do we land on tails when we flip a coin, what we could do is flip that coin 100 times and just see what happens. But obviously that's going to take a lot of time. Often we don't want to use that time, and it's not super accurate. It's not going to happen every single time. So typically what we shoot for is what's called the theoretical probability. And this is a probability that is calculated using a mathematical model rather than an experiment. So instead of flipping that coin, we're going to crunch some numbers to figure out what that probability would be. And in general, the probability of an event A, that's our notation here, P of A, that's probability of event A, it is equal to the number of outcomes in A divided by the possible number of outcomes on the bottom. So if we're talking about flipping a coin and we want to know what's the probability of getting 10 tails out of 20, then we would say, oh, we landed on tails 10 times, that's event A, that would go on the top, and we flipped a total of 20 times, that's our outcome on the bottom, so that would be 0.5. 10 divided by 20 is 0.5. When it comes to calculating probabilities, in addition to crunching numbers, oftentimes, if possible, we want to create some sort of diagram to go with our probability. Some examples we're going to see in class are a tree diagram, a Venn diagram, or some other visual representation of our situation. And really, this just comes down to practicing, seeing different types of problems, and then as you get more familiar with it, it becomes much more clear what type of diagram to use. Oftentimes, when it comes to probability, we're not dealing with just one event, so we're not just flipping a coin. Sometimes we have two events or even more events. So what we say is that if we're given two events, call them A and B, maybe it's flipping a coin and rolling a die, then the probability of A or B, we use the notation of a right side up U, and that stands for OR. So that's the probability of A or B. Whereas if we want probability of A and B, that is denoted with an upside down U, probability of A and B. And if you're familiar with Venn diagrams, you probably know that AND is the intersection of the two circles in our Venn diagram, whereas OR, that is the overlap of both of them. So if I asked you, are you in orchestra and on the football team, that's going to be a very exclusive group of people, right? Because you have to be in both of them. Or if I said, are you in band or on the football team, that's a much more inclusive term. You could be in one or the other or both. So just know the difference between and or. They really are pretty different from one another. One helpful probability requirement is that any probability of any event has to be between 0 and 1 inclusively. So using our notation for any event A, we could say 0 is less than or equal to the probability of event A is less than or equal to 1. And if it's equal to 0, that means that that simply cannot happen. And if a probability is equal to 1, we say it must happen or it will happen. Another property we have of formal probability is that if we add all of the possible outcomes together, then the probability of those outcomes has to add up to 1. So when we're flipping a coin, all the possible outcomes are flipping heads and flipping tails. There's not really another option. So if we add the probabilities of those two events up, obviously that's 50% and 50%, add those together, it has to be 100%, okay, or 1. One of the most useful properties of probability is called the complement rule. And this tells us that the set of outcomes that are not in the event A is called the complement of A. And how we denote that is kind of with a little exponent with C. That just stands for A complement. And the probability of an event occurring is 1 minus the probability that it does not occur, okay? So if the probability of me passing the AP exam is 0.8, then the probability of me not passing the AP exam is 1 minus 0.8 or 0.2. So the complement rule, maybe not so useful right now, but as we get into more complicated probabilities, keep this in the back of your mind. It's really going to help us out a lot. The fourth property we have with probability is called the addition rule. So before we dive into the addition rule, let's talk about the idea of being disjoint or mutually exclusive. They're exactly the same thing. So if events that have no common outcomes, they are considered to be disjoint or mutually exclusive, okay? So what I think of is back in middle school, remember when they only said you could be in choir or in band or in orchestra? We could consider those to be disjoint events because back then you were only allowed to be in one of them. It was not possible for you to take both choir and orchestra. So if any two events cannot happen simultaneously, they are considered disjoint or mutually exclusive. So with that in mind, with the idea of disjoint or mutually exclusive events in mind, the addition rule tells us that for any two disjoint events, A and B, meaning they can't happen at the same time, the probability that one or the other occurs is just the sum of the two individual probabilities. In other words, probability of A or B is equal to the probability of A plus the probability of B. Now, keep in mind, this is only valid for disjoint or mutually exclusive events. What we're going to see in our next chapter is if we do have an intersection in our Venn diagram, or if the two events can happen at the same time, we have to add a little bit more to this formula. But if you're provided that the two events are disjoint or mutually exclusive, just add them together. That's your probability. Now, this next rule we have, again, this is simply for special cases. It's called the multiplication rule, and it is only valid if we have events that are independent from one another. So think of flipping a coin, or if you draw a name out of a hat and put that back in. So if we have two events that are independent, call them A and B, then the probability that both of them occur is the product of the two probabilities. In other words, the probability of A and B is equal to the probability of A times the probability of B, only in the case that A and B are independent. One other part of our multiplication rule is that two independent events, so again, one does not influence the outcome of the other, they are not disjoint if the two events have probabilities greater than 0. And one last thing that I'll say about what we've said so far in probability is that many statistics methods require an independence assumption, but oftentimes we can't really assume that events are going to be independent at all. So before you dive into it, make sure you think about whether that assumption is reasonable before you use that multiplication rule. So make sure that they're truly independent events before you just go ahead and multiply. So when we go to a problem and we try to put these rules to work, in many situations, we're not just going to use one of these properties, we're actually going to use a combination of them. So keep that in the back of your mind. Like I said, you always want to draw a picture if you're able to do that, or if it makes sense in that problem. And it's always a good thing to remember that it's easier sometimes to work with the complement rather than the actual event. So here's a quick example. Once I'm done reading this, go ahead and pause, think about it, and then I'll go over the answer. So Mitchell recently turned 18, so he plans on winning the lottery. He plans on it, doesn't want to, he just plans on it. He plans to increase his odds of winning by selecting ticket numbers that have not been picked in a long time. He says that in the long run, every number should be selected equally often, so this is the best method to win. Is this a reasonable strategy? So pause, think about that for a moment, and then I'll go over the answer. So the answer, of course, here is no. The law of large numbers is only going to work in the long run. Obviously, if Mitchell is selecting a number, that's a very short-term thing. Long run is very different than just what's happening in that moment. Random methods used to select lottery numbers have no memory of previous picks, so they're independent. And so there is no increase in the chance of a certain number being picked. So even though the number 5 might have shown up in the past 10 lottery picks, that does not decrease the likelihood that it happens again. On the same note, if we haven't seen the number 10 in 3 years, that does not necessarily mean it's going to show up in our next lottery pick. All right, so let's try number 2 here. Again, when I'm done with this, go ahead and pause the video, think about how you might solve it. So in an effort to gauge people's opinions on Paramore's music, Tyler randomly selects phone numbers from the phone book. Using this method, he reaches 76% of the people he calls. Given this information, find these probabilities. So basically what this means is that once he makes a call, 76% of the time, somebody's going to answer the phone, okay? All right, so take a moment, try to calculate these. So given that, what is the probability he successfully contacts the next household on the list? So just the next house, what's the likelihood of that person picking up? Letter B, what's the probability he successfully contacts both of the next two households on his list? Letter C here, what is the probability his first successful contact is the third person he calls? And then finally, letter D, what's the probability he makes at least one successful contact among the next 5 people on the list? And my hint to you is that if you call one person, that does not influence the likelihood that the second person would answer. So they are independent events. So take a moment, pause, see if you can come up with this. Okay, hopefully you had some time to do that. What I would recommend, what I like to do with this sort of problem is what's called the blank method, and I'll explain that as I go here, okay? So the first one, probability that the first caller picks up, that is just 76%. There's nothing really going on there, just 76%. That is our provided information. Now, if we want to know for letter B, what's the probability of success of 2 consecutive calls? Well, because those are independent events, we can just multiply them. So what I mean by the blank method is I'll draw a blank, then I'll draw another blank, and then I'll put the probability of each event on those blanks and then multiply them together. So the first one, 0.76, is the likelihood that they answer. Then the second one, probability that the second one answers is 0.76. So the probability of both of them being successful is just to multiply them. In this case, 0.577, or about 57%. For letter C, if we want to know the probability that the first successful call, or the first person to pick up is the third person he calls, we would use, again, that blank method. How I think of this is we're going to call 3 people. The first person is not going to answer. Second person is not going to answer, and the third person is going to answer. So here, that's where the 0.24 times 0.24 times 0.76 comes from. The first 2 people are not going to pick up, and the likelihood of each of those happening is 0.24. Remember the complement rule, 1 minus 0.76, that would be 0.24. And then that third person is going to pick up, so that's where the 0.76 comes from. So if you multiply all those together, or if you prefer to use this exponent notation, 0.24 squared times 0.76, here we'll get 0.0437, or about 4.4%. Then finally, on letter D, if we want the probability of at least 1 out of 5 people answering, what I like to do on this sort of problem is if I'm talking about at least 1, think of how many people that includes. So at least 1, if we're talking out of 5, that would be 1 person, or 2 people, or 3, or 4, or 5 picking up out of the 5 people. Well, what we could do is find what's the probability of 1 person picking up, then add that to 2, then add that to 3, then add that to 4, then add that to 5. But that's going to take a lot of time. So in this case, I think it might be easier to use that complement rule. So instead of finding the probability of 1 or 2 or 3 or 4 or 5, we can take 1 minus the probability of 0 people picking up, okay? And that's what I've outlined here. So 1 minus the probability of none out of 5 answering, that is 1 minus 0.24 times 0.24 times 0.24 times 0.24 times 0.24. In other words, 5 people are not going to answer. So if we take 1 minus 0.24 to the power of 5, we get about 99.9%, or 0.9992. So if we call 5 people, the likelihood of at least 1 person picking up, it's pretty much guaranteed. It's 99.9%. Okay, so when it comes to probability, more than any other unit we're going to talk about, it really does just come down to practicing and practicing more and practicing more. So stay diligent, stay on top of the work we're doing in class, try to stay on pace, and I think that it sequences very well. So we kind of build on what we know to get a little more complicated as the unit goes on.